Hi, everybody. I'm Mike Morrow. I'm the president of the St. John's Center of the RESC, and I'm just going to share my screen now, see how this works. And so that looks like the one we want there. So this is, oh, I got to click share. Okay, so this is the agenda more or less for tonight. We're going to hear from Rick Goulding about the James Webb telescopes. We're going to get some observation reports, some Christmas gift suggestions, the sky this month, and a couple other little things. Before we get started, I'd like to do a land acknowledgement. We respectfully acknowledge the province of Newfoundland and Labrador, of which the city of St. John's is the capital city, as the ancestral homelands of the Beothuk. Today, these lands are home to a diverse population of Indigenous and other peoples. We would also like to acknowledge with respect to the diverse histories and cultures of the Mi'kmaq, Inuit, and Southern Inuit of this province. We have a number of visitors with us, and I'd like to welcome them. If we were meeting in the chemistry and physics building, we would have a round of introductions, which doesn't work as well on Zoom. But I just want to mention that we meet the third Wednesday of every month, other than July and August. The meetings are open to the public, so if you want to join future meetings, you just do what you probably did this time, which is email info@stjohnsresc.ca to get the link. But if you're interested in becoming a member, we'd certainly welcome that. You don't have to be an expert astronomer. You don't really even need to be much of an observer. You just have to be interested in astronomy. I'm sort of on the beginning end of the spectrum, or maybe intermediate now. But some of the benefits include a supportive community. If you want to learn how to learn something about astronomy, or learn how to use your telescope, if you get something like that eventually, there's lots of people here who are happy to do that. And eventually we'll have things like workshops to help with that. We have a member chat group, which people post their observations, their pictures. There's lots of discussion. If something interesting is going on, that gets posted there. That's a nice benefit. There are some great publications from the RESC. There's the magazine Sky News, which I think, as sort of a popular astronomy magazine, is probably one of the best around. There's also an RESC journal. So both of these are every second month. The journal is a little bit more academic, but not that much. There's a fairly blurred line between the two publications. And the Observer's Handbook is a real gem. It's got all sorts of information, gets updated every year, so you get a new copy. At the center, you have the opportunity for about $10 a month in most cases to rent a variety of telescopes. There's a solar telescope, there's accessories. That's a good way to find out about what you might want to think about if you're preparing to buy a telescope or something, and a lot of us have done that. And hopefully pretty soon we'll be able to get back to doing member observing sessions in Butterpot or other places. You can join by going to the RESC website, resc.ca. I've got a link here, but I'd suggest that if you are joining, you also send a message to info@stjohnsresc.ca, so that Randy, who's the secretary, can keep an eye on things, and especially if you're having trouble registering, send something there. So we'll start Rick's talk in a second, but before we do, there was one other interesting thing, or one other quite pleasant thing that happened in the last week. Gary Diamond, our current past president, has been a member for at least 50 years. And last week, Randy and I met Gary at the Johnson Geo Center and presented him with what this is, and Jim Johnson's going to talk about this a little bit later on. This is a print on aluminum of the Heart and Soul Nebula. The picture doesn't really do it justice. It's really quite spectacular. And we presented that to Gary, and along with a plaque to go on the print, which says, with thanks for longstanding commitment and contributions to the St. John's RESC. And very appropriately, the print is of the Heart and Soul Nebula, because Gary's been the heart and soul of the operation, or at least one of them, for a long time. So that was very pleasant, really sort of my first task as president, and I enjoyed that quite a bit. So with no further ado, we're going to go to Rick Goulding's presentation on the James Webb Telescope. So Rick's going to tell us some stuff that he's learned about the telescope. And Rick is a longtime member of the Department of Physics and Physical Oceanography. I guess it's not telling tales out of school to say about 35 years, right? And he has an interest in amateur astronomy, but he's also very active in outreach and spreading the word about science. And so with that, I'm going to stop sharing and invite Rick to start sharing and start his presentation when he's ready to go.
Okay, hi everybody, just give me a second. Let's hope I got the right one. Okay. Everybody see my James Webb Telescope, an amateur walkthrough? Good, Mike?
Yep.
Okay, good. Okay, so let me begin. Okay, so my interest in the James Webb Telescope came a long time ago when I first heard about it. And I've sort of just been following it along as it's being built and delayed and delayed and delayed. And Mike, when I mentioned it to Mike that it was going to be launched on December 18th, Mike said, why don't you give a talk about it? So give me a good idea to put together some of my sort of half thoughts about this thing and to learn a lot about the James Webb Telescope. So I call my talk an amateur walkthrough because I'm by no means an expert. My background is as a laser spectroscopist, so I do have quite a background in spectroscopy, but that's not the emphasis of this talk at all. So I'm as amateur as everybody else, but hopefully I can transfer some good information about how this whole project worked, because it was an enormous project. So let's go and see how everything works. Okay, so the James Webb Telescope, short name for it is JWST. There's a very good chance that that name's going to be changed in the next little while, because apparently James Webb did some inappropriate things that are probably going to change the name. One of the thoughts about James Webb is that it's the successor to Hubble, but it turns out, yes, in some ways it will be the big successor to Hubble, but it's really a successor to Spitzer, which is a telescope that I'll talk about on the next page very briefly. It's a combined NASA, European Space Agency, Canadian Space Agency project. It was conceived in 1996, so that's like a long time ago. And the current launch date is December 18th, in about a month from now. The cost, $11 billion US. 11 billion. It's almost as much as Muskrat Falls. The builders are Northrop Grumman. They're famous for building a lot of fighter planes and anything high tech that goes into space, I guess. And Ball Aerospace. I really don't know much about Ball Aerospace, but their name pops up quite a bit. So let's go back, and before we talk anything about comparing it to Hubble, let's talk about the Spitzer Space Telescope. That was launched in 2003. It's the range of wavelengths that it sees is about, it's all in the infrared. It's 3.6 micrometers out to 160 micrometers, which is sort of the near infrared. So it's looking for things that are warm. It orbits, and this is significant, it orbits about 600 kilometers above the Earth. And that's more or less in the same, that's sort of space shuttle type orbit. So you can get to that telescope if you wanted to, or if you really needed to. The instruments it has on board are infrared cameras, infrared spectrograph, and some kind of multi-band imaging photometer. Its successes were the study of many galaxies, lots of galaxies, and the discovery in particular of Earth-sized planets. And I guess the biggest one was a a star that was 40 light years away. So they found Earth-sized planets that far away. It ran out of helium in 2009. So once it runs out of helium, then basically the problem is that the detectors can't stay cooled, and you can't see anything. It kind of goes blind. So I guess it's still up there, just floating around in a bit. So that's the Spitzer, right? So it really is, when you see some of the characteristics of the Webb, you'll see that it's really the big brother to this one. The problem with Spitzer, of course, before we go any further, is that it's so close to the Earth that it's seeing heat everywhere. That's one of the big problems. And the other problem is that it's not shielded from the sun in the same way that James Webb will be. So it's kind of like the first generation, that one. So the James Webb consists of, and you've all seen pictures of the James Webb. It has a primary mirror that consists of 18 segments. They're gold-plated beryllium, and the beryllium is there because it's light. It turns out it's also bendable. You can bend it a little bit, and that turns out to be significant in some of the ways that it's designed. It has the primary mirror has a diameter of around 6.5 meters. So that's like 20 feet. It's a big, right? Big guy. The Hubble, by comparison, only had a 2.4 meter radius. And the light collecting power typically goes as, A squared, and the A is pi r squared. So you can kind of see the big advantage that James Webb has in terms of light collecting power. It's designed to observe from 0.6 microns. So that's just a little bit farther than, red. It's basically red, out to 28.3 microns, which is, quite far out. So visible to mid-infrared, they call it. The Hubble, by comparison, went from 0.1. So it saw visible out to 1 micron. So it basically was a visible, very near infrared kind of thing. So it didn't really see a lot of really hot objects. The James Webb, because you're looking at things that are cold and you don't want to see any other heat sources, you don't want to see yourself sort of being hot, it's going to be kept below 50 Kelvin. And the way they're going to do that is they're going to use, that's one of the reasons why they're putting it where they are, but also it's going to have a big sun shield that sort of goes between it and the sun. And so it's going to be able to look at things that are really cold, or it's not going to be bothered by all the warm things around it, better way to say it, right? And one of the significant things about the James Webb is going to be positioned at this L2 Lagrangian point, which I'll talk about in a second. And basically, you can see at the bottom, I've written that it will be used to observe high redshift objects that are too old and too distant for Hubble to observe. So later on, we'll talk about the kind of things that James Webb will see. So the primary mirror, I thought I talked about it. I know that some of the astronomers in this club have made their own mirrors and bought mirrors and every other thing. So I thought I'd spend 2 slides talking about the primary mirror. So the primary mirror is gold-plated beryllium, as I said in a previous slide. Beryllium is flexible and lightweight. It has each of the 18 pieces is hexagonal, so that means it has 6-fold symmetry. Now the reason for that is that when they put it together, they can fit them together without any gaps. They can also sort of make if you look at it, like a rough spherical surface out of this. It turns out that there are 3 optical, for lack of a better word, prescriptions. So in the picture you see A, B, and C segments. They all have slightly different sort of natural curvatures to them, and to try to give us the shape that in the end we're going to want. And that's going to be a circular mirror with a well-defined focal point. So this is what one piece looks like. So imagine face down is the gold part, and you can kind of see here that each of the mirrors, and this is, I hope people can see my mouse. You can see that there's basically 1, 2, 3, at least 1, 2, 3, and then a 4th motor in the middle. So I don't know if you can see but if you look at where all the struts come from, there's also a motor there. So that apparatus sits down on the back of the mirror element, and the 3 motors allow it to change the shape of the mirror very slightly along those 3 motor sort of directions, and also in the middle. So it can kind of take this thing and flex it. It can flex the mirror, each element, to try to bring it into shape. And not only is that an incredibly powerful thing to be able to do, it's also a very good way of, fixing your focus. But it's also very complicated. And that's the thing I think to take away from it. So it's not just a bunch of gold 18 gold pieces of mirror stuck together. It's 18 active pieces that are active in many ways and can change their shape, sort of like shape changers. So what's the mission objective of the JWST? The objective, one of the primary, there's a bunch of objectives, I guess. I don't know if it's fair to say one. So it's going to look back in time around 13.5 billion years. So that's much closer to the time of the Big Bang, which is like roughly, we estimate at 13.8 or 9 billion years. So it's going to look back in time quite a ways. And the idea about looking back there is that you can look at, that's when we think galaxies and stars started to be formed. And so you can look at very old galaxies and stars and star formation from the beginning. The whole idea being to get an understanding of how these things were formed and and in relation to where things are now. The James Webb, because it's an infrared telescope, will also be able to look into and through some interstellar dust clouds. So that's going to be important in that if you're looking at the formation of planets and stars, if you look into the dust clouds, that's where they start. That's where most of the stuff we think starts, right? And the last thing, but not least thing it's going to do, it's going to look for and study exoplanets. So when we talk a little bit more about the type of instruments, you'll see how it can look for, Earth-like planets, basically. So it has four, I don't know if you can call these four distinct primary missions, but I think that you can kind of say that. Just checking my time now. Oh, I forgot to start my time. Okay, so those are the mission objectives. If we look at this picture here, and if you can see my mouse, can you see my mouse? No? Okay, so if you look at this picture, you can see about, let's go halfway across the picture from the right. You'll see it says first stars and galaxies. And on the bottom of this picture, there's a scale, and you can see where the 1 billion year scale is. So that's about how far back we're going to look with the James Webb telescope. There's still about, 250 million, 300 million years from the time of the Big Bang, but it's quite a bit farther back than what Hubble could see. So if it gets up there and starts working, it's really going to probably, much like Hubble, change the way we look at the universe and everything like that, and what we know about that. So it has an incredible potential to probe far back in time, but still, it's still a ways to go before you get to the beginning. So as we said before, the JWST was a product of three main organizations, but there were a whole lot of players in this. In fact, if you start digging deeper, you can see that some of it was made in the Netherlands, some of it was made in Canada, some of it was made in the US. So the bits and pieces came from everywhere, but they were assembled in a place called Redondo Beach in California. And in the picture, you can see it's in the top left. And then it was put on a boat and taken down to French Guiana, where the Ariane 5 rocket that it was going to be launched in is located. So it had to go through the Panama Canal. And so it was a long, long trip. By this time, it's already been tested. It's ready to go. It's just an unfortunate fact that they had to move it to a really far away place, right? Here's a picture of the boat that they have it on. You can see it's kind of located at the front of this boat. I can't really tell where it is in this picture, but in the right hand side picture, you can see the telescope container in the front, and in the background is the Ariane 5 rocket that it's going to go in. And I'm not sure if I mentioned this anywhere else in my talk, but one of the reasons for the shape, the 18 hexagonal type of pieces for one single mirror, is that this thing had to be folded so it fits into the nose cone of that rocket. And so the only way to do it was to fold it. Initially, they had way more pieces for the mirror, but costs and everything else, they finally settled on 18. So it's folded so that it'll just fit snugly into that nose cone of that rocket. So it's there. It's been there since, I think, October, not sure, 18th, something like that. And this is the timeline from then. So if you look at so this only takes a second to go through, but it's an interesting slide, I think. So it arrived in the rightmost, since you can't see my mouse and I don't know how to fix it at this point, in the leftmost part of the slide, you can see that 55 days it arrived at the dockyard, let's say. And then not much happens. 29 days, the main stage is positioned somewhere, and then it's not placed onto Ariane 5 rocket until 7 days before launch. And then they close it up, and at one day they roll it out to the launch pad, and then they launch it from, T = 0. They launch it from French Guiana into the on its mission. And so then the last 4 little things or 5 things on the right just tell you that 2 minutes you get booster separation, so that's going to be traumatic. It's always a lot of vibrations and stuff. Then at 3 minutes you get fairing separation, so the nose cone basically opens up. You get main stage separation at 9 minutes. At 27 minutes the rest of the ship kind of drops off, and then at 30 minutes, sort of approximate time, the Webb Space Telescope goes off on its own. And I'll have a better picture of that, but just to give you an idea that a lot of stuff happens at the launch in the first 30 minutes. And the telescope has to be designed so that it can handle this kind of vibration. And you can imagine that's not easy. So apparently it was tested and retested and tested and retested and tested and retested. So hopefully they got a lot of redundancy built into it. This is the timeline, and without my mouse, I feel like I don't know what to do. But I can just talk us through the slide a little bit. So this is the basic timeline for the launch, and you can see that a whole lot of stuff happens in the first 30 minutes, as is listed. But at 120 minutes, the antenna assembly comes out, and so then it can start sort of transmitting back to Earth. But the interesting things is at 2.7 days after launch, it starts to deploy the sun shield. And so the James Webb has a 7-layered sun shield that unfolds over, if you look at this picture, about roughly 2.5 days or so. And it's 7 layers. It's about the size of a football field, apparently, when it unfolds. And you can imagine thinking of it as mylar, 5 layers of mylar separated by, some small distance. There's 5 layers so that, each layer, so the layer that's facing the sun will get hottest. The one next to that will get much less hot. The one next to that, much less hot, much less hot. So that when it gets to the 5th layer, the telescope, where the telescope is just beyond it, the temperature will be okay. And you can kind of see that stuff happens for about, the secondary mirror assembly the mirror assembly and stuff doesn't occur until much later on. So there's a little thing in the bottom that says primary mirror backplane assembly that occurs at 7.5 and 8.6. And that's kind of when the telescope is really just finishing putting itself together. So one thing to take from this slide is that a lot of stuff is happening. Apparently there's at least 60 major events that have to occur between launch. And when it gets to this point on the bottom right-hand side of the screen, which is L2, that will be its orbit point. So that occurs, roughly, we'll see in the next picture exactly when it occurs. So it's a complicated process for sure. So the James Webb Telescope, and it's not going to be very mathy, so don't anybody worry about this, but as a physicist, I couldn't resist. So the L2 point you can see in this picture is far right. So the picture on the bottom there, you can see is far right. So the sun is in the center, then the Earth is, you can see the picture of the Earth there, then outside its orbit is L2. L2 is 1.5 million kilometers from Earth. So it's like really far away. And so if anything goes wrong with the telescope, there's nobody going to get it or fix it. So that's why, unlike the Hubble, they managed to do a couple of missions. Because Hubble was in low Earth orbit, they managed to do a couple of missions so they could get up and kind of fix it. So that's the kind of scheme here, right? That's where L2 is. Now, if you look at the math of it, though, if you actually look at it, I was kind of surprised because this is a Lagrange point, and Lagrange solved these equations by hand. And if you look at it, you can kind of see there's not that many numbers and not very many parameters. So it is possible to do it by hand. Not that you'd want to do it, but it's possible that you could actually calculate some of this stuff out. And that kind of surprised me. So this is for L2. There are other stable points, as you can see in this picture. So you could put your object in one of these other points, L1, L5, L4, and L3, but you'd put them there if you had a different mission or a different type of telescope and that kind of thing. The whole idea here is the L2 point is, as you'll see in the little video I'm going to show you next, it's a point where the orbit will be stable. And as the Earth, and here's the important part, as the Earth goes around the sun, and then the sun is kind of moving as well, the space telescope at L2 will follow the Earth in its orbit around the sun. So the Earth is always more or less between it and the sun. And the effect, the physics of it is that the gravitational pull of the sun and the Earth can keep that thing in a stable orbit and give it the same orbital period around the sun as the Earth. So it always tracks with the Earth. And that's no mean task, but that's what the definition of an L2 point or Lagrangian point is. You can see the picture here, and I'm going to show you in a second, another video, but what the thing to take away from this picture is that if you look at where the Earth is and the sun is, you can see that the L2 orbit looks like it's almost perpendicular to the page. And in fact, that's what happens. That's how you can get a stable orbit and kind of make it work. It's kind of a squiggly orbit, but basically it's like turning an edge of a Frisbee side on. So it's kind of a funny thing. So here's a little video. I hope it's going to work.
Where Webb's orbit around the sun is synchronized with Earth's. This point, 1 million miles from Earth, Webb is free from the thermal influences of Earth and all its Sun, Earth, and Moon. The brightest objects in the sky are hidden by the deployed sunshine, giving Webb a dark, cold, stable environment to carry out its mission.
Oops, but you could see from that little video that as the telescope goes around, follows the Earth around its orbit around the sun, that it's not a simple orbit. At one point, it takes kind of a big dip, and that orbit is called a halo orbit. It's kind of surprising that it is stable. And one of the things that will limit the life of Webb is going to be it has rockets on board that can adjust its position once in a while so that it stays in that L2 orbit, because it's not possible to put it there perfectly and keep it there. So eventually those rocket engines will run out of fuel, and that's what will limit the life of Webb.
Rick, there's a question.
Yeah.
Was the L2 point selected also for communication stability, or is that a factor?
No, I don't think that's a factor at all. I think it's mostly, well, I guess it's a factor in the sense that you want it to be close enough to Earth that it's easy to communicate, right? You know, but one of the things you want, I guess I don't know the answer to that, but I would say, thinking about it, that it's probably true, because what you want is two things. You want to be able to have your heat shield so that as the telescope goes around its orbit, its back is always to the sun, so the heat shield is always protecting it, and you don't want it too far away from Earth so that you can communicate with it. But I'm not really sure about the answer to that, but it kind of makes sense that it would be. Mike might have some thoughts on that. I don't know. But it's a long way from Earth. It's 1.5 million kilometers from Earth. I should have calculated how long it takes for a signal to come from there, but not that long, but it's noticeable probably. Okay, so the orbit is a funny orbit. It's kind of like a Frisbee on side going around with the Earth, as you might like. And let's see now. Okay, so so this is, in a previous slide, I kind of gave you a quick look at what happens to it as it launches into orbit, and then sort of a quick idea of what's going to happen as it gets out to the L2 point. But now I'm going to show you a little video, and this is a great video. It's better than any slide could be. It shows the timeline to full operation. So I think it's around 2 minutes long, so it's not too long, but I found it very kind of interesting. I don't think I can talk over it. I don't know if I can or not, but if I can, I will try. So 31 minutes after launch, solar arrays. So it gives it powers. So first course correction. Then second course correction, 2.5 days. So the sun shield starts to unfold, 3 days. So this is the cool, complicated, one of the cool, complicated parts. This takes about 2.5 days. Here's kind of an interesting one. They put out a stabilization flap just to sort of keep the sunlight off it. So the sun shield is like a mylar sheet, but 5 of them. So now they're unstacking, separating themselves. So there's the mirrors coming together. So there's no separation between the hexagonal pieces. So contact with Earth. So there's the sort of vertical frisbee. So the temperature is only about 40 degrees above absolute zero for some of the mirror. So this is where the little motors come into place, tweaking every piece of the mirror. So 180 days after launch, 6 months before it's kind of ready to, 6 months after it's launched, it finally is ready to collect data. So it's a super complicated process, super complicated device. And if anything doesn't work, nobody can go to fix it. This is what amazes me. Okay, so this is just a slide with the timeline. I'm not going to show you this slide. I just put it up there to show you there's so many, it goes from 27 minutes when the telescope separates from the launch vehicle to, it takes almost 6 months, 180 days. So until everything is ready to go. So scientists at home are on Earth waiting for this thing to kindly work. They're going to be busy, but they're not going to know if it really works until 6 months down the road. And so many things that could not work right. So complicated. Okay, so I'm going to talk very quickly about, or in a few slides, about the sort of the integrated science instrument module. And I don't know a ton of stuff about this, but I have been reading a bit about it. And so there's 4 main instruments on this telescope. The first one is called a NIRCam. It's a near infrared camera. And the University of Arizona built this one. There's the fine guidance sensor, it's near infrared imager and slitless spectrograph. You'll see that's called a NIRSS, I think it's called. That's the Canadian built one. And so that's a kind of an interesting device. Then you have the NIRSpec, which is a near infrared spectrometer, and then you have the mid infrared instrument. So they're all built by different people. So ESA stands for European Space Agency, NASA. This is sort of a subset of NASA here. I forget what it's called now. So basically 3 main organizations that are involved. So this instrument, so this is the first one. This is the mid-infrared instrument. And this is the instrument that has the biggest, if you look at this little picture at the bottom of the slide, this instrument has the widest response range. It goes from 5 microns all the way out to 30 microns. 28 microns exactly, and it's built into channels so that it's possible to turn off one channel and just look at a very small part of the spectrum. So it's kind of its broadband instrument. It has to be cooled to 7 degrees above absolute zero, so that's pretty tricky. So it's got to be kept away from any sunlight behind and sort of live in its own little thermal world. The idea for it is that it's going to look at redshifted light from distant galaxies, young stars, and just the formation of comets is sort of a secondary thing that it might look at if they get a chance. I mean, basically, they're going to use these instruments for whatever they can. By Canada being involved with the building of their part of the instrument, apparently you get dibs on looking time sort of thing. This is a picture. I put these pictures in, or the bottom picture on the right, in to show you the size of the scale of the instrument. So this is about how big it is. And almost all the 4 instruments are roughly this kind of size. They're kind of complicated looking, and they have a lot of different components to it. If you look at the top picture here, this is where the light goes in through the thing that's sticking out in the front left, I guess, and then it bounces around inside, and it analyzes the light. So that's the MIR one, so mid-infrared instrument. Then there's the near-infrared camera, and this is the primary imaging device for the telescope. So this is the one that the other ones will all sort of piggyback on top of this one, and it goes from 0.6 to 5 microns. So it goes out only into the near infrared. It doesn't go as far as the previous instrument. It'll look at light from young stars in the Milky Way and beyond as the stars are in the process of formation. And one of the things it does, it uses coronagraphs to study dim objects near bright ones. So you can imagine all a coronagraph is, the idea is that if you have like a sun, you kind of put something up in front of the sun, try to block that as much as you can so you can look at something that's orbiting near it. And one of the ideas for that is to look for, of course, it's another way of trying to look for exoplanets, but the coronagraph idea is unique to this particular instrument. And as you can see in the picture in the bottom right, this is the optics picture of it. It's very complicated. It's a lot of pieces. And so it had to be tested very hard, I think, to get it going. So that's the near infrared one. Then there's another one. The names all look almost the same. This is the near infrared spectrometer. And it does, if you look at the range over which it works, it is about the same. It's 1 to 5 microns, but it's sort of a medium resolution spectrometer. And so it's looking at the same wavelengths, but in a kind of a different way. And its idea, again, is to look at the early universe, how galaxies are assembled, birth of stars. And one of the things that makes it different, though, than the previous one, and this is the important thing, is that if the telescope were going to try to look at a big piece of sky, it would have to collect for a long, long, long time. And if they wanted to focus in on a small part of the sky, then they're not looking at the rest of the sky while they're doing that. And that's kind of the nature of telescopes. But what this thing does is that it can look at 100 objects sort of at once, or in a 9 arc minute square. And the way it does it sort of takes that little square of the sky, and it has a little shutter system, and it just closes off, sort of like when you put your finger in front of your eye, you can look at, different parts of what's in front of you. And that's what it does. So they developed this technology they call microshutter technology. So they can only look at a little bit of the sky, of the total sky that they're looking at, and then send that into the spectrometer. And that's what makes this one different than the one before. And they have a thing called high slit spectroscopy mode that they'll look for transiting exoplanets. So when an exoplanet passes in front of a star, you see a changing in the dimming or change in the spectra of the star very slightly, not very much. And you can use that to kind of look and assume that there might be a planet there. So that's the second one. This is the Canadian one. And the Canadian one is kind of an interesting one, because what it does, it allows the James Webb telescope to point precisely. So if they're looking at something and they want to line up on it really good, then this is the instrument that they will use. It's also used apparently for determining where the Webb telescope is. I'm not sure how it does that, but it's kind of an interesting thing. It can track moving objects, so it can actually track things. So it obviously has a sophisticated electronic system in it. It goes about the same range as two of the others. It goes from around 0.8 to 5 microns, so into the near infrared. And its main purpose, and again, these are all going to be used for sort of different things, but the main reason for having it there was to look for exoplanets. So by being able to point the telescope very precisely, they could look for exoplanets and using the same technique, one of the same techniques we talked about, where if the planet goes in front of a star, it changes the spectra very slightly. And then if they do find an exoplanet, they can use the FGS in combination with the slitless spectrograph to try to look at the atmosphere of that planet. So again, this is about the size of it. The picture that's on the right, they're all around the same size. You notice that they're all coated, they're covered, they cover them with a very thin metal film to protect them from the heat. So heat is the biggest kind of player. So if you put them all together, this is kind of what you get. You can see that some of them overlap. The near infrared camera and the NIRSS, they overlap. They go from about roughly 0.6 to 5 microns. It's only the mid-infrared one that looks far out into the infrared, so out to about 28 microns. So some of the redundancy, you might say, well, I have 3 of the instruments looking at the same thing, but you're using them for slightly different things. And I guess every of the 3 players, they all had kind of different interests. So it's pretty sophisticated altogether. And I think, so this is my last slide actually. So I try to keep it pretty short. So what's the mission lifetime? Well, the minimum is 5 years. They're kind of hoping they might get 10. But what will happen is that it will run out of fuel, as I mentioned before. It'll run out of fuel to keep the orbit tweaked. And so once it does that, then it's just going to drift and eventually just go off into space, right? It's too far from Earth to fuel or repair. One of the things that's kind of mentioned in a few of the web pages that I looked at and things I looked at is that they tested the beryllium mirror, the gold mirror, against micrometeorites. But nobody really knows how this thing will hold up in space to that kind of thing, because it's a pretty sophisticated instrument and has lots of motors, it has lots of electronics. So I think only time will tell if it's going to work. What fascinates me about it is that, it's a $10 billion project. They've been working on it for 25 years. It's going to be launched on hopefully December 18th or so. And but it'll be kind of 6 months before you really know it works. But if you'll know in a month whether things are going good, or I guess in a few days. So pretty exciting, I think. And like Hubble changed the world. There's a picture of Hubble's picture in the top here. 2 famous Hubble pictures. The one on the bottom is one of the deep sky pictures, and the top is just I didn't know what that one's called, but they're also pretty to Hubble. And so the low resolution spectrograph on the James Webb will produce pictures like the Hubble, the top one. The other ones will be a little bit different. So I think we can hope that this could be the next telescope that can change the world. So that's it. That's my little walk through the James Webb telescope. So
Okay. Thanks a lot, Rick. You hear me clapping anyways.
yeah, good. Thanks.
And I'm sure Rick would be happy to answer some questions. You can either put them in the chat or you can use the reaction button to put your hand up, and we'll see if you can unmute yourself. If you can't, then I'll figure out how to do it. And do we have any questions? I can start with a question. Rick, in your reading about it, did you come across any information about how smooth the mirror had to be? Since it's infrared, presumably not quite as smooth as you need for visual, but
no, in fact, I read a lot, and now that you mention it, it never mentioned how flat it would need to be, because it's infrared and because they're going out to 30 microns. The 30 micron stuff doesn't need a flat mirror at all. It's only the like the 1 micron stuff will need some flatness. But the only thing I can say about that is that when they tested the mirror's assembly, they somehow loaded it so that they could simulate, or counteract the effects of what gravity would do, sort of what they tried to do with the Hubble. But no, I didn't see anything. I think a lot of it is going to be determined by how well the motors can pull those segments into the shape that they want them. I think that's a big factor.
And all the little latches unlatching. There's a couple hundred of them, or
Oh, the little motors, you mean?
the little latches.
Which latches do you mean?
Oh, well, the latches that are holding it closed right now have to. There's
Oh,
apparently a lot of them that
yeah.
all have to let go at the same time.
Yeah. I don't know too much about that part.
Okay, so Jim Johnson hopefully has not jinxed it. He said Hope Ariane 5 maintains its successful launch
Yeah.
record.
They were worried about the shields not detaching because the second to the last one, the shroud didn't come off properly, I think, but they tested that again recently and it's okay for go.
Yeah.
Rick, with only 5 years of life, is there another telescope in the works? I haven't heard of. In
Nothing
5
that
years,
big.
yeah, 5 years is
Yeah,
going to come
yeah.
pretty quick, right?
Yeah, but they don't have a way. I guess they don't have a way of. They didn't have a way of putting more fuel on it, and that's the big player here, right? It's not that the instrument is going to be no good. It's just that they don't have any way of putting fuel.
Is there
more
no
fuel.
other fuel they can use? Like
I'm
is
sure
all-
yeah.
yeah.
I'm sure they've optimized it down to
Mm.
the ounce, right?
Well, you can get
So-
Elon to drop off some fuel on his way to Mars or something, right?
Yeah, there you are.
You could do that.
Here's another question. Is this the first time we have sent probes instrument packages to a Lagrange point?
No, there's been a bunch out there. There's a couple of telescopes that are sitting. There's one at L2 now, or near L2, or was at L2, and there are a couple things already at Lagrange points. So it's not a new thing to do. I can't tell you what the name of the telescope is right now, but it has been done before. The thing about it is that it's a pretty stable point, but it's not stable, because the dynamics of all the, like, you got the Earth and the Moon and the Sun pulling on this point. They're the three closest things. That orbit is going to be, half stable, but it's going to need to be tweaked once in a while. So the idea is, if you put something there and you can't correct its orbit, you will eventually lose it.
Okay, and Chris Stevenson says he's going to hold his breath for the next 2 months. So
Yeah, I don't
he
think I'll.
apparently wants us all to do that, but he can do it and let us know how it works out.
Yeah, it's going to be. Imagine if you were involved in that project. It would be so stressful.
Yep. And
Yeah.
Jeff asks, are there particular targets for exoplanet exploration or just aimlessly looking?
I'm sure that they have very specific targets, because they already know where there's some exoplanets. So I'd say that they'll look at, not only will they look for new ones, but they'll look at the ones that they've kind of identified as possibilities. This instrument's going to have so much more resolution than the Hubble because of its size, that they'll have a close look at anything that they had as candidates before, and then they'll go looking for other things.
Yeah, I think that's true.
Yeah.
Chris said, Chris is answering the question about things at the
L2 point.
other L points. Chris, did you want to unmute yourself for a second and just say, I don't know if, yes, you can.
I can't talk much because I'm in a room here
Okay.
with other people. But we've got things at Lagrange points. And the thing that comes to mind, I need to check this, but I'm pretty sure there's a pair of solar observing probes, stereo A and B, which are at the L3 and L4 points on Earth's orbit, ahead of and behind the Earth. You remember that diagram that Rick showed with the triangle shapes, Sun and Earth at two of the vertices? Yeah, and the third points of those equilateral triangles on the orbit, that's the L3 and L4 points. And that's for looking at the Sun from, where the Earth is going to be in the future and where the Earth was in the past, right? Because 3 places along Earth's orbit at the same time. And there are likely many other positions because they're quasi-stable. And my comment about Actually, maybe I shouldn't, because I should let you read ahead.
Okay.
Yeah.
And we'll wrap it up with this. The last question was from Jim Johnson. Would not ion propulsion be an option to maintain L2 stability? And
I think that one of the answers, so one of the things you got to think about is that this telescope was designed in 1996, or it evolved from a 1996 design. So the technology, some of the technology that's being used is still a little tiny bit older technology. And while an ion drive might be, or something like that might be possible, we don't have that. It's way too primitive for us to think about using that right now. It'll be another 30
okay.
years.
Well, there's a couple more messages saying thanks for an interesting talk, and certainly I echo that. Thank you very much, Rick. And
Yeah, I hope you enjoyed it.
okay, so if you would stop sharing your screen.
Okay.
Okay, so what we're going to do now is go on to some member observations, and I'm going to I've got them on my computer, so I'm going to run through them. And what I've done is I've asked some people to talk for a couple minutes about to pick something specific from things that I mined off of the RASC talk mailing list. There are more pictures than that, so some of them I'll just sort of introduce myself, but the people that I've asked, or the pictures that people have selected to say something about specifically, I've indicated with an asterisk. So people can see says member observations now. Good. Okay. So I've sort of gone through in chronological order. So one of the ones I picked out was from Jim Stacy, a full moon just about a month ago, and that was handheld with his camera, and that was a Hunter's moon, and we're going to hear from Jim again in a minute. And now I'm going to invite John Peddle to unmute, and he reported visual observations on Uranus, Ceres, and the Triangulum galaxy, and he's just going to talk a little bit about how he finds those and using some stellarium stuff. So John, are you there?
Yep, I'm here.
Okay, so the first one up, I guess, is Ceres. So go ahead and
Yep. Well, first of all, I'm a member of several like Facebook astronomy groups and mailing lists, and between those and the Sky News magazine, there's many ways to find out what's of interest in the sky each night. And one of the big things now is that Ceres is next to Aldebaran, the constellation Taurus. And Ceres is the largest member of the asteroid belt, but is not always easy to find. So we had a clear night last week, so I went out with my binoculars. Taurus and Aldebaran were in a very good position, easterly and a bit above the trees. So I pointed my binoculars at Aldebaran, and right next to it in the same frame, same field of view, was a point of light exactly where Ceres would be. And I always want to be absolutely certain that what I'm looking at is what I think I'm looking at. So I changed the magnitude limit in my app a few times to make sure it was Ceres, not another star that was nearby. And there was nothing else nearby, so I was definitely looking at Ceres. It couldn't have been simpler to find.
that's pretty impressive with binoculars.
Yeah. Yeah.
So good time to look for that.
15 by 70 binoculars, actually.
Good.
Yep.
Okay. You want the next one?
Yep.
Okay, so
And
this
then I
is
remember-
Uranus.
Yep. And then I remember Uranus was nearby in the constellation Aries. So I tried for that one too. I could see the main stars in Aries, Hamel and Shiratan, fairly clearly. And I could tell by looking at the app that Uranus was directly below Hamel. So I sent it on Hamel, and just a bit below it, and you can see in the picture there, there's a perfect triangle of stars. So I found them quickly enough. And then it was just a matter of moving the binoculars down the exact same direction a bit more. Then I came to a diagonal line of 4 stars. And the second star from the right was Uranus. It was very, very easy to find. Just almost as easy to find as Ceres. So
And
Von
is
Hamel,
it pretty close to the horizon at this point, or?
no, it was, I guess, like about 10 or 10:30. Like it was maybe not quite 45 degrees up, I guess. Like it was
Okay.
clear, it was clear of the trees I had, and no trouble to find it. I had clear view of it. So you see Hamel there and see the perfect triangle, like 3 stars below it. So I found that and then moved straight down. And like I often hear, you might often hear the term star hopping to describe tracking down an object, but for me it's more like star pattern hopping. Like I'll find something, then I'll see a group of stars nearby, like that triangle, or stars in the letter T, and then I move on to another group of stars. And then I keep jumping around like that. Patterns of stars are easily to identify and more dependable than just single bright stars.
Yep.
Okay.
Okay, and Triangulum Galaxy.
Yep. So after he rained down, I tried to push my luck and look for the Triangulum Galaxy. It was the same part of the sky, and I could see the constellation Triangulum easily enough. So I started out at the rightmost star, Mott Allah, I guess, and hopped to where the galaxy should be, but I couldn't see it. I knew I was in the right spot because it wasn't far from Mott Allah, and the stars matched what my app was showing. But the constellation itself was just too dim for my binoculars. I was just up against the limits of what my binoculars could show me at that point. So, like, not every time you go hunting, you're going to track down your target, I guess. I needed something a bit more powerful.
Okay, great. Well, thank you very much, John.
Yep. And one more thing, like,
Oh.
like right now, Sirius and Uranus are still close to where I found them last week, and they're still pretty easy to find if you go looking. So I found them easy enough, and it's pretty easy to find if you get out now this week, say.
Okay, good. Well, that's some encouragement for everybody. So I'll thanks a lot, John.
Yep.
And so Chris, do you want to say something about this picture,
Yeah.
or do you want me to talk about it?
No, that's okay.
Okay, there you are.
My voice may be booming in this room. I apologize. Yeah, the night before Halloween was clear. A lot of us were out. John just talked about star hopping to Uranus. This is clearly taken with a larger telescope, not binoculars. But believe it or not, I have a small, one of these digital astronomy cameras with a 50mm lens on it as a finder scope. So I have its pictures in one of the windows on my computer, and I have another window showing what Stellarium predicts it to see, and I can actually star hop with that camera arrangement. So I literally star hop the telescope thing. So I started at Hemel and star hop down to Uranus at about 11 o'clock at night, and it was well up in the sky. So it's not a problem, as John was saying, to find. So the picture was taken through the main telescope, of course, with a planetary camera and a Barlow to push up the magnification. And Uranus is surprisingly bright in even binoculars. But so I could record it at 15 frames a second, use video techniques to take planetary pictures. And I recorded a couple of 2-minute videos at 15 frames a second to get a bunch of frames. Well, the gain turned up a bit, so Uranus registered in each one. Then I did 2-minute clips for the moons, but I used 2 seconds per frame because they're a lot cleaner. I only got 61 frames per clip for those. And I reduced the Uranus picture and the moon pictures separately. And then I put them together in a clever way so that the properly exposed Uranus was in the middle and the properly exposed moons were on the outside. And not all the fainter dots here are moons. So the 4, 2 above and 2 below are, and good Lord, I think it's Ariel. Sorry, it's, I sent along a Stellarium picture with this, but it's not here.
It's over on top. I've got it at
Ariel, and then
over on Ariel, Umbriel, Titania.
Umbriel and Titania is the bottom of the 4 dots nearest. People might recall that everything in the Uranus system is named after Shakespeare's Midsummer Night's Dream play. The other dots are stars, and to put this into context, the star on the bottom right is a magnitude of about plus 14.5. So it's all pretty faint. Yeah, so that's how I managed to pull that off.
Okay, thanks a lot, Chris. When that appeared on the group, everybody was pretty impressed, and I'm glad you were able to tell us about it.
Yeah, thank you.
Okay.
It turned out I'm happy. It's the first time my getting the moons actually, if you're honest. So I was quite pleased.
Yeah, first time most of us have seen something like that. Here's another one from, so thanks, Chris. There's another one that Chris did, I guess, the same night.
Yeah, and
Probably a little less challenging.
much the same technique. I started the evening on Jupiter. We have trees blocking the southern sky now. They've grown up. So my window for observing Jupiter is defined by when it crosses through a narrow gap between two trees. I managed to capture it before another Zoom meeting that evening. And it turned out to be okay. Yeah, that's not too bad. There's detail, and there's, I think it's Io on the left, on the right, and Ganymede on the left. I'm not sure. Somebody could check it. I've forgotten which of those two moons there are.
Okay,
No,
thanks a lot,
Europa.
Chris.
It's Europa on the right. Yep. Okay. Thanks, Mike.
Okay, so Jim's going to talk about this picture of the Heart and Soul Nebula in Cassiopeia. So is Jim out there somewhere?
Yep,
There he
I'm
is.
here.
Okay.
Okay, can you hear me, Mike?
Yep.
Okay, the details of how this picture was taken are basically in the print there. So I'm not going to talk too much about that. But I guess the Heart and Soul Nebula are, I guess, a showpiece. But what really impresses me about these nebula in Cassiopeia is just how large they are relative to the moon. I mean, and it's so large that I had to basically stitch two photographs together with taken with my 500mm wide angle lens, which I think, as far as telescopes go, 500mm is starting to is a fairly wide angle lens. So the nebulosity here is enhanced by the filters that I was using, which are basically a narrow band filter called the Optolong L Enhance filter, which is a tri-band filter. It passes H alpha primarily, and H beta, which is a blue-green or green-blue, and oxygen 3, which is either green-blue or blue-green. But in this particular image, we're seeing mostly H alpha, and that comes out as mostly red. But the Heart and Soul being the nebulosity is clustered around open clusters. So for example, the Soul Nebula, which is the baby-like image in the bottom left, there's actually two little clouds of nebulosity, which are basically surrounding open clusters in that nebulosity. And basically it's the wind from bright stars that basically like a stellar wind that basically blows the gas away from the stars itself. And the stars in some of those open clusters are very large. They're approximately 50 times larger than our sun. So and in the very center of this picture is there's an open cluster right at in the very middle. That's what I use to anchor as an anchor point for these two overlapping frames. I basically use the open cluster in the very center to be the central point of these two frames. Towards the right is the famous Heart Nebula, and there's an open cluster at the center of that, and a lot of dust and gas and so on to basically star forming regions. And that's the open cluster in the Heart Nebula is called the Malot 15. And towards the upper right, you have the Fish Head Nebula, which is actually the brightest part of that of this nebula, and it actually has its own designation as an NGC number, but it's colloquially called the Fish Head Nebula. And there's lots of other nebulosity in here which I haven't been able to identify, but I guess it's a very romantic sort of object, and I was very happy to get a couple about 2 hours on each of those 2 frames, and then managed to figure out how to stitch them together in PixInsight. So that's basically my background to this particular object.
Yeah, there's another one from Jim. This is his ring nebula with his 4-inch Maxitov. And as what I was saying was, this is always a crowd pleaser, a planetary nebula. The next one, Randy can say a little bit about this. A number of people took pictures on November 3rd, which was, I guess, a day before the new moon. And it was labeled as the toenail moon on the chat line. So Randy, did you want to say a word or two about this one?
Not much other than that we were lucky to have some clear mornings, and a lot of people saw that, and they were impressed by the earth shine. Just looking at the sky, you can see the earth shine. So if Twitter is anything to go by.
Yep. Okay, thanks a lot. And so Randy and Jim also took these pictures, and I guess you can you see my mouse on there at all or not? You can, okay. So this is the same morning, and Mercury's in the picture. There's Mercury there if you have a nice screen and good eyes. And so that's in Jim's picture. I'm guessing that's Kitty Vitty because that's close to him. And Randy got Mercury in a tree. And there it is down there, just next to the eave of the house there. So that was that same morning. And then here's another picture from Jim, which is the my control seems to be covering up the top of it, and you're probably seeing that, but maybe that'll go away in a second. That's the Pac-Man Nebula, and used, I guess, the same lens that he used for the Heart and Soul Nebula, and this one was November 6th. And then there were a number of pictures taken on November 7th. I don't quite know how to make that go away, but of the moon and Venus. This was in the evening. So here's a nicely focused one from Chris Stevenson, one from Gary, and this is one that I did and Cynthia did with her cell phone. Hers was a little bit earlier in the evening. So those are the and so next we've got Robert, and on November 9th, Robert went out to a secret place on Salmonier Line and got a picture of the Flaming Star Nebula in Auriga, and with just a few subs. But the one he's going to talk about also that night is the Iris Nebula, from the same place, the same night. So Robert, do you want to unmute and say a little bit about that? Is my control showing up on the top of the screen? Do you see that?
No,
Oh, good, because it's in my way, but it's not in your way.
no. Yeah, I don't have a lot to say about it, but it's just a few, 5 subs there. But each of them were 5 minutes in length, so 25 minutes in total through a 5-inch refractor and an ASI 2600 Astrocam. No post-processing, just the stitched together or stacked together subframes for that particular nebula. And I wanted to catch that one because well, I had never done it before, and I knew that I was hoping that, you know, the blue would come out because you don't get to see too many nebulas with blue in them. So I guess I was rewarded there with that. So that's all I have to say.
Yep, lovely picture. I love the dust dye. The blue color is really neat, and the dust is very nice too. So I think that's the observation reports that we've got. And so the next thing we're going to do very briefly, I hope, is some Christmas gift suggestions. So, or holiday gift suggestions. And I've asked a few people to talk about them. And there's some books and some other things. So I'm going to ask Randy to talk first of all about the one that I've asked for from Santa Claus. And Santa Claus was just laughing in the background.
Yep. Can I share my screen?
Oh, sure. Go ahead.
Okay.
So I'll stop sharing. There we
can you-
are.
Okay, so this is the backyardastronomy.com site, which talks about that book. There's lots of copies on Amazon. According to my research, there's none at Costco at the moment. There's one at Chapters on Kenmount Road, if you get there in a hurry. This is by
Okay,
far the,
Cynthia's leaving right now.
yeah, this is by far the best astronomy book that's come out. He's got everything in it. It's geared towards most of us, right? Binocular astronomy, and shies away from, you know, the using Pix Insight and stacking and all those sorts of things for the more, well, although it's covered. So like I said, these are the chapters. I hope it's not going too fast. And it's current and up to date. Like I said, if you're any aspect of astronomy you want to get into, that's what's there. His website, by the way, is called Amazing Sky. So I'd encourage you to go there. It's a little bit on processing, but it's well worth the money. Okay, is that it for that?
Yep,
Amazing
and,
Sky, Randy.ca or .com or
What?
I guess
What is-
some are searching Amazing Sky then.
My cursor is covered up by the thing, so yeah, it's backyardastronomy.com.
yep. Okay, so the next one that I asked Randy to talk about was solar astronomy. Do
Okay.
you want me to share that screen?
I can do the same thing if you're interested. Just
Sure. Yeah. Okay, you go ahead and do yours then.
so I just happen to have all these things lined up. I found this publisher called Axel One, and these are European publishers. So this is the one on solar astronomy. Anybody's into solar, again, it maps out, and it's 480 pages. You know, 1,500 images. It covers everything that you can imagine. If you're interested in solar, there's the 2 chapters, right? They have another one on planetary astronomy, same sort of thing, right? Contents, and these are some of the images you can see in there. Anyhow, I'll again, you had to look that up on the solarastronomy-book.com and order it online. I've never seen any of their books. And usually I bought this through Facebook, and I usually don't buy things through Facebook.
Okay, that is 69 euros.
Yep.
So,
So 100 and some odd dollars, yeah.
okay, so the next thing is Jim Johnson there. He was going to say a little bit about how you can get images printed on aluminum, like the one that we presented to Gary, and he might say about how you could get one of his images printed on aluminum. I'm not sure. We'll see.
I'm
So
here.
are you there, Jim?
Yep. Yeah. Can you hear me?
Yeah, you're a little quiet, but that's okay.
First time I've heard that in a long time. Yeah, so I've been dealing with these people now for probably the last 3 or 4 years, and have had numerous orders of prints from them. So they're a fairly reputable company. They're located in Ontario, I believe. Pretty sure that's where they are. But yeah, that's where I usually order all my prints. I've been kind of a very, very minor side business, just selling prints to mostly coworkers and stuff out here who have been interested in obtaining prints for gifts for mostly their better halves. So that's about it.
Okay, thanks very much. And I'll just say that, seeing the print that we gave to Gary in person, it was really quite remarkable. The detail and the quality of the print was really amazing. So Robert, can you talk about keeping your feet warm, a perennial favorite on the list?
Yeah, well, it's quite important to keep your feet warm. And in the wintertime, that's hard to do if you're out at scope. So I think we all know about the hand warmers and such, but feet warmers or foot warmers is, something that is not as well known, I guess. So I find that the full-sized foot warmers, it says they're available at Canadian Tire, but I've seen them at the dollar store, Dollarama, I'm sorry, and I'm pretty sure Mark's would probably have them. And I previously purchased a set of rechargeable insoles a few years ago from Mark's, but I haven't been over there in a while, so I don't know if they still carry it or not. I couldn't find anything online, but that doesn't mean that they don't have them there. And I found those were pretty good. Little rechargeable battery fits down actually in the sole and keeps your feet. Well, it helps a lot with keeping your feet from freezing up. And the other thing, of course, there is available at Mark's is the socks, the electric socks, and you can see on the top cuff there that's where there's a little battery holder. Looks like it's got a flap, so you would take it out, I guess, and recharge it. And another way to keep your feet warm. So it's an important thing. That's it.
Okay, thanks a lot. And the Marcellus is going to talk about a new development, some classic books that have become available again. So you want to unmute, Marcellus?
Yes. Okay. How's this going to show up? Wilman Bell, they've been hard to find for a while. Apparently, the American Astronomical Society has taken over all their stock and have taken over their titles and contracts with their authors. So they're re-releasing a pile of stuff. It's mostly available on the Sky and Telescope websites now. They got one like Craig's the Dobsonian Telescope, Star Test and Astronomical Telescopes. A couple there that you can see that Mike has up on the screen now. My favorite is this one right here, the Messier Marathon. If you don't have a computerized scope, I think it's one of the best books around for how to find your way around the night sky. See how this will show up. It shows you, whoops, okay, that's not going to work. How things would work on whether it was a right angle finder scope or a straight through finder scope. It shows the different orientations of the stars and also what the circle of your Telrad or your Rigel Unity finder would show. Like that Messier Marathon one, I've seen that for over $100 on eBay, but right now it's back to a normal price. So I think it's $25 or $28 or something like that on the Wilman Bell or Astronomical Society site. Definitely some books worth checking out if you're into books and not apps.
Okay,
That's
thanks a
about
lot, Marcellus. And the last one I just wanted to mention, Many of you know about it. If you're using a DSLR and you want to get more of the red H alpha, sometimes people remove an infrared filter, and sometimes people do it themselves if they're a lot braver than me. But this outfit, nightskycamera.com, will do it for you if you want to send them a camera. But they also have some used cameras where it's already been done, and they are selling. They don't have a lot of them. There were more when I started looking at this. 2 of them are sold, so I guess each listing is for a specific camera. But they have a deal with the RESC until the end of the year. RESC members can get a discount. So they're in Vancouver. So I just thought I'd mention that. So that's what I had for the holiday stuff.
Mike,
Yeah, Randy?
if anybody's missed all those links, just send a note to the info address and I'll send you all the links if you're interested, in case you didn't see them as they went by.
Thanks a lot. That's a good idea. And so now, Robert, do you want me to put up the sky this month, or did you want to share your screen with it?
No, Mike, you put it up.
Okay, so take it away, Robert, and I'll just advance when you want me to.
Okay, Mike, thanks. We'll go through this quickly. As we all know, it's online on our website, so you can peruse through that at any time. So this just shows the timing of twilights and when it begins and ends, and civil and nautical being just manifestations of how far through the sunset or sunrise that we are. And one thing to note is the 9 hours and 11 minutes. So we can see that we're definitely into the winter time of the year. Go ahead. And here we have the best time to look at the planets when it crosses the meridian there, for example, and what the sun is doing right now. And you can see that there's a couple of small spots there. So if you get a chance to get out with a solar scope, have a look. And if you have a solar scope for prominences, I'm sure you'll be treated with a few. Next.
Okay.
Okay, all night planets and evening planets and morning planets is pretty much self-explanatory. However, at the bottom there, we see rare event. A partial lunar eclipse will occur on the morning of November 19th for St. John's. Begins at 2:32 a.m. and ends at 7:20 a.m. So if you can't sleep, or if you'd really like to see this eclipse, then you see the timing there, and the maximum obscuration, there you go, that's my eyes, I suppose, at 5:32, and total time 4 hours 48 minutes. During maximum eclipse, the moon will be in the west. This is a near miss eclipse with the moon being covered 97%. So it'll be interesting to see if and how much the moon changes color with it being so close to the total eclipse. So we will hopefully get some reports on this if we're going to be lucky enough for it to be visible.
Can I add something, Robert? The current forecast is for a bit of snow earlier on. Don't let that deter you. You also don't need to stay out for 4.5 hours. It's only about 30 minutes or so of any real usage. You know, the preumbral part is, you won't notice it. And I think the sun is pretty well up by the time it ends for us. So we'll see what happens. Right? The current spot wicks says it should be clearing before 5 o'clock for us. So keep an eye on the weather. Yeah.
Okay, thanks a lot. Okay.
And here we have comets that are currently visible with optical aid and asteroids. And we had a series visually from John earlier there. And that's certainly something you should look for if you got a pair of binoculars. Shame on you if you don't.
And the Comet Leonard is, people are starting to post a lot of pictures of it, but it's pretty low for us, right?
Yes, it's very low to the horizon, unfortunately, but still could be something to look forward to around about what I saw in early December to mid-December to late December, I guess, as being, you know, the peak. I can't remember exactly when the peak is predicted.
It says December 14th.
Yeah, but that depends on outbursts, and you never know when an outburst may happen. So just keep looking.
Okay.
Meteor showers, I think the Leonids is just about now, is it? Yes. Knew I read that somewhere.
Gary was telling us that.
Yes. And deep sky objects for November, December for telescopic and binocular, should you wish to have a list of well-placed objects to go for, then look no further than this publication.
And here's our observing challenge.
Yeah, to try to see at least one more than the usual 6 stars in the Pleiades cluster without optical aid. In most cases, most people can see 6. However, in excellent transparency and dark sky, some can see 9, 10. Record is 18, held by Walter Houston. Anybody want to take on challenge and see if they can do 19? And International Space Station timings, and our observing sessions are currently canceled due to COVID. So we'll hopefully get back to those sooner than later, but it's kind of hard to say when exactly that will happen.
Okay, well, thank you very much, Robert. So we're just about finished. I just had a couple of oh, sorry, I jumped the calendar, but we can probably figure that out. It tells us when the next meeting is, which is going to be December 15th. So there is a calendar there. Sorry about that. So the last item I had was just a little bit of news. And there it is. We're going to be sending out a survey. It's anonymous. It's when you get it, it's a Google survey, and it's just to sort of get some feedback from members. So try and do it in a couple weeks. It shouldn't take you very long, but there is room for you to make some suggestions about things you'd like to see in the meetings and things you'd like to see the group doing. We have been, for the observing reports, been mining the RESC talk groups.io, whatever it's called, but not everybody subscribes to that. So I'd encourage you to send observation reports and photos to info. Oh, that should say photos. I screwed up. Photos at stjohnsresc.ca, and that I think will be in the email that Randy sends out as well. And so it can be observation reports like we heard from John tonight. If you'd like to talk about something, you can send that in, and that'll sort of flag it. And the other thing is, I'd encourage you to think about giving a talk. You don't have to be an expert in something. You can give a talk basically about what you've learned about some topic, and it's a good way to learn something about a topic. So don't be shy about volunteering. If there's something you're interested in learning about, I'm sure we'd be interested in sort of following what it is that you're learning about that topic. So,
Mike,
yeah.
Doug would like a minute to talk about the committees.
Oh, please go ahead, Doug. So I will stop sharing this and go ahead, Doug. There you are.
Thank you very much, Randy and Mike. So I'm just doing a call for volunteers for the Light Pollution Abatement Committee and the Dark Sky Preserve Committee. Just a moment to describe what they are. So the Light Pollution Abatement Committee, it advocates locally for the reduction of light pollution and its detrimental effect on human health, the environment, and the night sky. The committee meets at the most, I would say, quarterly, or as needed. And committee members evaluate opportunities to reduce light pollution and cooperate with organizations to encourage responsible lighting practices. In the past, we've had about maybe 5-6 members on the committee. And so we just look generally around the community for opportunities to advocate for light pollution abatement. So the reduction of artificial light and lighting of better quality. So that's one committee. And there's another committee that sort of flows from this Light Pollution Abatement Committee. It's called the Dark Sky Preserve Committee. So Dark Sky Preserve Committee assists the Terra Nova National Park with its Dark Sky Preserve designation. This is a designation that was earned by the park and granted by our society, the National Society of the RASC. The committee promotes the reduction of artificial lighting in the park and encourages the park to educate and promote the reduction of light pollution to the public and nearby towns and municipalities. And that committee meets quarterly or as needed as well. So 2 committees, one flows from the other. Looking for anyone who would like to volunteer on these committees. The Dark Sky Preserve Committee is focused on one object right now, which is Terra Nova National Park. And we liaise with the park, with their staff. Some of our members actually go to the park and look at the lighting, and they assist the park with advice on lighting practices. You don't need to be an expert on lighting or light pollution to participate on these committees. If you're interested in the topic at all, we will bring you up to speed on the necessary things that you need to know about light pollution. So if you'd like to volunteer to assist with the Light Pollution Abatement Committee or the Dark Sky Preserve Committee, or both, just let Randy know and I'll be in contact. Thank you.
Thanks a lot, Doug. So I guess that's sort of the end of the formal meeting, but we can have a few minutes to sort of chat if people want to turn on the cameras and unmute. And Randy's going to use Skip the Dishes to send us all a coffee and a donut, right? So
I posted
anyways,
if I could mention, there was last night and this morning at a peak of the Leonids, and somebody posted a video that they took last night driving west on the Outer Ring Road. Just a short fireball. If you're interested in that, her Twitter handle is Nolene Anthony.
so this is another way we could do astronomy. We can get a dash cam and just drive up and down the Outer Ring Road for 8 hours a night. And
You mean you aren't out?
Having
You
an
aren't
all-sky camera, right?
You aren't doing that? Oh, I might mention Dave is not on there now. I don't think his all-sky camera has been active for the last 2 weeks because I was checking it last night, and so that's where I went to look.
I put up my camera. My camera runs 24 hours, well, 12 hours a night.
Yeah.
And it's on the international web. It's hooked up to 200 plus other cameras from all over the world. So if you want to look at shooting stars, it's the place to go.
Did you get the fireball last night?
I got a fireball. My time, I guess, would be more accurate because it's controlled by the guys. Randy said they said around 7-something, 7:10 or 7:05. So I don't know if I was looking in the same direction. I'm looking west. And if you go to that site and you go to the back a couple of days, you'll actually see what areas I cover. I cover about 100-foot radius, 100-mile radius or 100 kilometers.
Okay.
But I'm the only one on the island right now doing that. So that's hooked up to the global meteor network. If you go back on my archives, I've got some great nights of meteor showers where there was like hundreds of shooting stars. And what really freaks me out is not just the, I have a video at the bottom, you can also go through the videos, but I can't get over the number of satellites that it picks up.
Yeah.
So my backyard, the camera now picks up down to 6 magnitude.
Bright.
And there are lots of satellites.
Oh, I can't get over the number of satellites. It's amazing.
And pieces of satellites.
Lights. Yeah.
Yeah.
But you can always tell the SpaceX ones because they seem to fly one after another. Boom, 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 boom.
The launch on Saturday, was it, or Sunday? They launched another 54, and it's in a new pattern. So this is their 4th pattern. So if you didn't see them before in part of the sky, you'll see them now.
Yeah, I used to have a site, and it's probably still around, where you could go to and put in your location, and it would work with Google and would show you the path where they would go right over your house. And I stayed up one night and there they were, right over where they said they were going. Be with buddy's house next door across the way. I thought it was kind of funny to take some pictures.
What Gary's referring to there is just after a launch, they just released a whole packet of these satellites, and it takes them a while to spread out. So if you happen to see them within a day after launch, it looks like a string of beads going across the sky. And we were fortunate to see the very first grouping of them back out.
And I thought it was the end of the world.
It was.
That's what it was, but I thought it
So,
was literally the end of the world. I'd never
Yeah.
seen anything like that.
yeah, it was quite
Don't they
amazing.
call it like a satellite train?
Yeah, but I mean, trains usually move fast. These were hardly moving at all, right? Anyhow,
I got a link here for that. I'll just post it here now where you can find the satellite trains like based on your GPS. I'll pop it in there now.
Okay, so you're putting it on chat?
Thanks, John. I probably got it on my computer somewhere, but my computer has gotten really funny. Like halfway through this show, this Zoom, my just shut down. And I noticed I getting emails that I thought I'd sent are now all in my draft. And Chris just sent me an email. He said, "Thanks for your thing, but that was 6 months ago."
Yeah.
So it seems to be sending things. I don't know what's going on.
Black Friday sales are coming up soon, Gary. For
Yeah, I think so. I think I'm going to have to.
Yeah.
Yeah, this is, well, actually it was kind of funny because I came in yesterday morning and it was saying Windows update, and then it said you got 32 drivers out, and then it started downloading drivers for me. I don't even have.
Yeah, I got a note. There's another release of Pix Insight, but I wasn't able to download it. So my system is stuck on the 20H2 Windows update. It's like 3 gigabytes or something, and it gets 92% of the way through and stops right every day.
Oh dear.
So.
I got a problem with my mail.
And
I
your
can't,
camera.
I can't receive it. But I had a spare Gmail account, and Randy, you sent me the link. That was,
Yeah.
otherwise I wouldn't have been here tonight.
There are generic problems with mail. Just yesterday or so, we had trouble sending out to our list, and our host provider was having trouble getting to Bell. I discovered after, it seems British Columbia is coming apart up there. If it's not fires or floods or earthquakes. And so I wouldn't be surprised if you'll be seeing more and more of these email disruptions. That's the name of the game these days.
And I see Joe Hodich here. Hi, Joe. From Earth Science, retired a few years ago.
Yep.
Back in town. This is the second time I've seen him today.
Yeah, good to see you. I
Hi, Joe.
enjoyed the talk. Yeah.
Hi, Joe.
Hi.
A few of you probably know, those of you with sort of earth science backgrounds know Joe.
Yeah, I see John Jameson's is on. Yeah.
Is he a rock hound as well?
Yep, he is indeed. Yeah.
Yeah, good.
Hi, John. Anyway, so should we wrap it up?
Okay.
Okay, well, thanks, everybody.
Thanks, everyone. It was a good one.
Okay,
Yeah, we'll
like I
see
said,
see you in a month.
don't get discouraged on Friday morning for the eclipse. I have a good view in my driveway. I might just sit in my car all night. I don't know yet. But there could be 5 or 10 centimeters of snow early on, and then it should clear off. And like I said, you don't need to be out. And there's only about 30 minutes or so that's really important. And we won't see the very end of it anyway. So there's no point of staying up, till the sun rises.
Can you
Just wanna
see it
ruin
if
my
it's that
sleep.
low from your driveway?
Yeah, it's actually quite high.
15
And,
degrees?
Yeah, I got a good view. There's no street light down that direction. So
Okay.
now I see John.
But
Nice.
I'd say hi.
Nice.
This is the first time I've joined one of these talks. I heard about it at MUN,
Good.
and I just thought really enjoyed it. So thank you.
Good, thank you.
Thank you for coming.
By the way, all of our lectures, Zoom sessions are on our YouTube page. So if you can find us there, you can see some of the past ones if you're interested. Phil McCausland has done an occasional lecture.
Yep.
See you all later.
Bye.
Okay, bye, everybody.
Bye, everybody. Bye, bye, bye. Here we go.